Welcome to Nextiva AI Paper Talks. I am Ruth Bella, and today we're going to discuss the AI research paper on improved noisy student training for automatic speech recognition. If you are into AI, if you want to learn about the math and the engineering behind it, then stick around because this video is for you.
This is a pretty technical discussion, so hopefully everyone will be able to get some core intuitive ideas. Those of you who know more about AI will be able to dig in a little bit deeper. So the paper that we're talking about today is Improved Noisy Student Training for Automatic Speech Recognition by Daniel Park, Yu Zhang, and a group of others from Google. This is from the Google Brain team. It was released in October of 2020. And actually, there's sort of three papers in play. The paper we're really talking about is the one in the middle, but it draws from some foundational research and that was really in image processing, and we're going to talk a little bit about that. And then there is a follow-on paper where the results were improved that I will talk a little bit about at the end. Let's jump right in. What is noisy student training? It is a semi-supervised learning technique. And it was initially applied to image classification. Very often, it's very common that a lot of the foundational stuff in machine learning started there. And a basic idea that was applied very successfully there is automatic speech recognition. So the basic idea is that you start with a teacher model that you train on labeled data in that kind of standard way. That's pure supervised learning. So you have a whole bunch of audio and then transcripts, and those are the labels for the audio, and you train the teacher model. And then what you do is you take an unlabeled set of data that you don't have, say in the case of transcription, you don't have transcripts for, in the case of images, you don't have classifications for, and you have the teacher sort of guess what the answer is and apply what we call pseudo labels to the unlabeled data. And then what you do is you take the initial labeled set and you augment it with the pseudo labeled set, and you train a student with that larger corpus of combined data. And then you iterate, you make the student into the teacher, and you keep going through generations of larger and larger samples, and the learning gets better. Now, if that's all you did, you would end up with a basic problem. When I looked at this initially and didn't look at the additional parts of it, I thought, well, that's kind of like in academia, we have a rule that you don't hire your own PhDs because you kind of get inbred after a while. And that's, you'd have a serious problem with confirmation bias and, sort of overfitting and not having your model effectively generalized if that's all you did. So what you do is you do two things. First of all, you're very selective in the pseudo labels that the pseudo labeled examples that you add to the augmented data. And secondly, you inject noise into the data that the student gets. So the student is not getting the raw input, it's getting input that has been, that has some noise injected into it. And so those are the two things that are different. Okay, so now we're going to talk, I want to motivate a little bit. Why would this work in automatic speech recognition? Why are we doing this, and what is, why is it sort of promising? And these are just intuitive ideas, and we'll drill down as we get into it. So the first is that most of the current generation of ASR models have an encoder decoder architecture where the sort of front end of the model just learns representations, good representations of the data that it has coming in. And then it passes these representations, the encoded representations, sort of standardized encoded representations, to a decoder layer that is what gives you the answer. So the whole point of the front end of the model is to reduce the dimensionality of the data. When you think about a stream of audio, audio files are large. They're large because there's huge amounts of data in them. And one of the things that we do in ASR, pretty much however you cut it, is we focus on reducing that dimensionality first. And the way that we learn how to do that is totally self-supervised. In say Word2Vec2, which is a contemporary model, they use masking to mask out little pieces of the input and then train the model to fill in the masked out pieces. That can be done totally self-supervised. So, well, how is that relevant to what we're talking about? Well, the relevance is that what we're doing in noisy student training is we're generating larger and larger samples. We're generating more data that we can put in. And just simply pumping more data through the front end of the model is going to improve the encoding. So that's sort of motivation number one. Motivation number two is that the errors that we make, that our models make in speech recognition, are often the result of either just slightly off pronunciation, accents, a little bit of noise in the recording, the pace and cadence being a little bit off. And so it makes good intuitive sense that if we teach our models to be tolerant to noise, then they're going to perform generally better. They're going to perform better when the representations that they get out of the front end are slightly off, and they're going to perform better when they have noise in the core data. Okay, the last piece is more relevant to the world of practitioners today, which is very often what we have is we start with models that have been trained with large amounts of labeled data, but that labeled data is something like pristine, like audiobooks and stuff like that, where you've got very nice spoken text and you train a model on that data, and it's very valuable to get those trained models. But then as a practitioner, what we're trying to do is we're trying to take those models and fine tune them and specialize them to our domains, maybe to somebody with a specialized accent, maybe to a different, actual subject domain. And if that's our problem, then if our mass unlabeled data set that we're using to augment the training of the model is from our domain, what noisy student training does as we iterate through that process is it gets more and more of that domain data actually in to influence the model. So this is just hand wavy intuition about why it might be something that would work for us. Okay, I'm going to talk a little bit of, what do you have to do to actually set this up and make it work in ASR? Well, first, you have to figure out how you're going to specify the initial model. What is the what's the start model that you're going to work with? And then you have to determine how you're going to create. When I said you start with a model and then you generate the pseudo labels, well, okay, you got a whole bunch of pseudo labeled data. How do you mix it in? How do you pick which ones to put in? And how do you make sure you're not really screwing up the sample? Filtering is where we're deciding which ones are good enough. Which ones does the teacher have enough confidence in? Balancing is where what we're trying to do is make sure that the student, doesn't get a diet of only broccoli and, no peas. Making sure that the data that the student gets is representative of, what we want the student to see. And then finally, you have to figure out how you're going to add noise. What's your technique for noising the data that you provide to the student? Those are really the practical things that that come into this.
Bill, sorry to interrupt. One quick question that I have, and I don't know if you mentioned this. Would these type of models would be considered only for audio signals, like waveforms, or in this case, is that what we are discussing?
Well, yeah. The topic of today is automatic speech recognition, which does deal with audio input. But you're exactly right that the technique could be applied to lots of different kinds of machine learning tasks. And in fact, the idea for it came from image classification. What's being applied here, and what's really cool, is when we get into how we inject noise, we just borrow shamelessly from what the image processing guys did. It was initially applied to image classification, where you say, okay, I want to know what is a cat, what is a dog, what different images are, and they found that by injecting noise and using precisely this technique, the algorithm that I just described, they could get significant improvement in the image classification algorithms. So this could be applied to lots of different things, not just What I'm kind of really drilling down in here is what's in the paper, which is speech recognition, transcription. But it's a very good point. It could be applied to lots and lots of machine learning techniques and algorithms. Okay, so let's talk about really how the algorithm works. And this is really right out of the paper. It's using the notation of the paper, and it's the notation that I will use throughout. So you start with a labeled set of sentences, S, and you have an unlabeled set, U. And then you also have another ingredient that they used here, and which is which plays an important role in the whole thing, is an external language model that has been trained on a separate text corpus. So you can view the LM as sort of the outside expert that's coming in, and it's also forcing the model to be perturbed as well as the data. This is a core kind of aspect of how we avoid overfitting and how we make sure the learning is real as you perturb both the model and the data. So, okay, so you start with an initial model that you train on the labeled set, and you use spec augment to already inject noise in that initial training step. I'll talk at some length about what spec augment is, but imagine right now that it's just a way of putting noise into the data. Then you take the model that you have trained, the initial starting model, and you fuse it with the language model. Now, I'll talk about what fusion is and how it works momentarily, but just imagine right now that what's happening is that model is sort of allowing itself to get advice from the language model when it's actually scoring sentences and doing its work. Then what we do is we take this fused model and we take the entire unlabeled set and we attach labels. We just have it predict. We have say, okay, go transcribe all this stuff. And it goes and transcribes all that stuff. And so now we have labels for all of the unlabeled data. Then what we have to do is filter down that pseudo-labeled data to the ones that we're going to actually present to the student. That's the filtering step. And we'll talk about how that works momentarily. Then we balance. I said before, another thing we have to do is we have to balance. We have to take that pseudo-labeled data, filter data, and make sure that it's balanced. And then we mix it in. And now what we've got is we've got filtered, balanced, pseudo-labeled data that we merge in with the original labeled set S. And then we take a new model of the same variety that the initial one was, and we train it on that larger sample, and we use spec augment to inject noise. And then we just go back up to the top, because now what happens is the student becomes the teacher, and we keep iterating this process. And at each stage, we're sort of fattening up the training set, and the model is getting better. And we eventually, at step 2, we say eventually performance isn't getting materially better, and we stop. Okay, so that's basically the algorithm. So a little bit of details which we'll dive into more. I mentioned spec augment. I won't say more until we get there. Shallow fusion, I'll talk about what that is. It's the way that the language model, that external expert, is kind of consulted by the model that is the teacher model. And then filtering is based on the fusion score. It's based on, we'll talk exactly about how that works. It is a measure of confidence that the model has in the labeling. And then balancing is based just on token statistics, based on just how often the tokens from the token set actually show up. You want to make sure that the augmented sample you give to the student has a token distribution roughly the same as the original labeled set. There's a couple other things that I don't really have time to get into, but they are used in the paper, and it's really kind of cool. I mentioned that this filtering, what it does is it selects only the ones that the teacher's most confident in. Say, I know how to solve this problem, I'll give it to little Johnny, my student. What happens is that initially it's fairly conservative. Only sort of the best examples are provided, but then as iteration continues, that filtering criteria is relaxed so that you get more and more data in. And then at the same time, to make matters even more difficult for the student, the augmentation strength increases over iterations. It gets noisier. The data gets even more noisy over time. let me talk a little bit about spec augment, which is, this is the thing, and Ruth, this is it's really cool because this is exactly taken out of image processing. The idea that it's a really cool thing that happens very often in machine learning, especially in a lot of basic ideas start in image processing and then take a problem that we have and we say, well, can we see our data as an image? Well, in this case, you precisely can't. What you're seeing pictures of here are what are called Mel spectrograms, which are images drawn from audio input. So on the horizontal, you have time, and on the vertical, you have frequency, and the brightness is the intensity at that frequency. And so you take an original, you look at a spectrogram, and then now what I'm going to do is I'm going to mess with it to confuse the student. The first thing is time warping, which is kind of cool. It's got time warping. You can, if you imagine the whole thing is like a sheet of rubber, that it's elastic, and imagine you put thumbtacks in that top picture. You put thumbtacks around like 5 different points there, and then you randomly select a point in the middle, somewhere in the middle, and you actually just tug it to the right or to the left. Actually, you can see that's what happened down there. Then what'll happen is the whole thing gets stretched a little bit. It gets stretched a different amount at different levels, because imagine you've grabbed that little piece and you pulled it over. It distorts the image. That's what time warping is. And you can think about, what's it going to do to the audio? It's going to kind of mess up the timing of the audio. And again, that sort of simulates the difference, some of the things that happen in recordings and the way that people talk. Frequency masking, that one's real easy to understand. You just block out some frequencies. That certainly happens when you have interference and other kinds of stuff in audio. And then time masking, you just block out a piece. So those are the core components of what we do to mess with the student. And they do, you can see intuitively, they do sort of simulate the kinds of things that might happen when either recordings are bad, or people's pronunciations are bad, people's pronunciations are a little bit off. And that's the core noise injection that we use. Shallow fusion is this technique when I said we've got to get our external language model to come in and kind of influence what the teacher is doing and what the teacher is giving the student. What it does is it basically the language model only looks at the tokens individually. So the expression here that is the shallow fusion score, the first part of it is just what the model itself does. It's your typical log probability optimization of what is the most probable token Y given the input that I'm seeing X. That's what the contribution of M is. But then in addition, what we say is I want you also to include a factor that is the weighted probability, the unconditional probability of the individual token in the mind of the language model. So it basically makes more likely tokens in the mind of the language model more likely. But notice that the language model doesn't even see X. So that's why it's called shallow fusion. And this is the way that the external language model comes in to kind of push what the pseudo labeling into something that's a little more reasonable for the student. Okay, filtering. I said intuitively we wanted to filter based on the teacher model confidence. How confident is the teacher in the transcription? Well, the natural way to do that would be to just sum the shallow fusion scores over the individual tokens in the utterance. So you say each one, I have a confidence that comes out, but the problem that there is a problem with that. Maybe I'll stop here and say, does anybody see what the problem is? Well, the problem with that is that longer utterances are going to end up overrepresented, because you see this thing's just going to get bigger and bigger. As if you have 8 tokens, you're going to have 8 terms in here, and these things are not log probabilities. So if you just use that measure, it wouldn't really work. It would be all you'd end up with is the longest things. So a natural thing to think about that's maybe a little bit better is, well, what if you just divide by the number of tokens? That would be better. But it wouldn't really be perfect, because you'd still be biasing. the longer things would tend to win because they have more context. So what they do is actually very clever, which is they want to say, they say, okay, what is my problem here? I want to get a normalized score that is adjusted for the length. And so what they do is they actually fit a model that predicts the shallow fusion score based on the length, and they use the standardized residual as the measure. Now, what does that mean? What that means is you look at a sentence or an utterance that has come into this thing. You look at it, you predict what its total fusion score would be based on its length, and then you say, well, how much is it significantly larger than I would expect of an utterance of this length, or is it less? If it was significantly larger, then I give it a bigger score, and it's more likely to end up in my filtered set. So this is a sort of a standard technique that's used in MathStat to normalize and to say, if my problem really is to find out what the best thing is controlling for these other things, well, I'll fit a model and I'll just look at where it is in terms of residual. It also has a nice property that the residuals tend to be normally distributed. Okay, so balancing. How does balancing work? Balancing is what we're trying to do here is we're trying to make the token distribution among the filtered set very similar to the original set. So the token distribution is like, tokens are little word pieces. You can think of them as words, but they're a little smaller than that, but you can think of them as words. So what we want to do is we want to simply make sure that that distribution that I provide to the student in the total combined sample is similar to the original unfiltered set. So how do I do that? Well, what they do is they resample from, start off with your filtered pseudo-labeled set, and you sample with replacement repeatedly and try to find batches of sentences to add that move the distribution in the direction that you want it to go. Well, what do you mean by move it in the direction that you want it to go? Well, what this is it's a combinatorial optimization problem. And the way that they solve it, and this by the way is from one of the references in the paper. This is sort of hand wavy described in the paper, but in reference number 5, it's a beautiful paper that describes how this was, how this actually works. It was originally designed for making phoneme distributions uniform, but in any case, the way that it works is that you define an objective set function, which says for this set of which is the sample, I want to optimize all of this. And the function that I want to optimize is I want to look at all of the frequencies of the tokens. The FIs are the frequencies with which token number I appears in all of the sentences in A, and pi sub I is the probability of that token in S. It's the target distribution. The pi sub i's are the mass points in the target distribution I'm trying to hit. And what's really cool here is that if you simply maximize that sum of products, then you are going to minimize the difference between the distributions. And it makes intuitive sense, because think about it this way. If you have large FIs where there are large pi i's, that sum is going to be very large. If you use your FI weight on small pi i's, then the sum is going to be smaller. That's a hand-wavy intuitive argument. There's actually a proof in the paper, and so what is proved in the paper is that maximizing that function J is equivalent to minimizing what's called the KL divergence between the desired token distribution and that of S. KL divergence is like Kolmogorov-Smirnov distance for continuous distributions. So it's simply a measure of how close discrete distributions are to each other. Now, this function J has a nice property that it is submodular, which means it has this kind of diminishing returns property. And that's the analog of convexity in discrete spaces. And that means it has nice optimization properties, one of which is that the greedy algorithm is near optimal for solving it. So what they do is actually the greedy algorithm. So what does that mean? What that means is basically that when we're trying to decide we start with a base set and we're augmenting it. We're trying to create these batches that we add, that we resample to add back. And what we do is we just look at the benefit of adding every single individual sentence, and we take the ones that give the most benefit. That's the greediness. That's the greedy algorithm being used. And what's kind of cool is, all the math stuff that says, hey, that's near optimal. You can't do much better than that. And you continue to do that until your distance measure gets small. And they add two little constraints there. One is that no sentence can be added more than twice. And then the second is you got to preserve the total number of tokens. Okay, so that's balancing. Now I want to talk a little bit about, the cash money, the results. What do we get from this? They did 2 experiments, and you see 2 pictures on the bottom. The first experiment is with this task of LibreSpeech 100A60, which means we take the LibreSpeech is an open source data set of recordings and transcriptions that are there are people reading text. There's a 100-hour. It's like 960 hours. There's a 100-hour subset that is designated as very clean. It's really nice, clean data. So what they do is they take the 100 and use that as a labeled set, and they take the 860 not as clean data, and they use that as the unlabeled set, and they apply exactly the algorithm that that I just presented. The other task is a much larger corpus, both LibreSpeech and LibreLite, where it's a little bit more balanced, and there isn't this distinction between the initial data set being significantly more clean than the other. And you can see that first of all, there's significant improvement overall over the state of the art, baseline work. What was then state of the art? It has advanced since then, and we'll see in the next thing that there's an advance has been made. And you have a bigger benefit in the non-clean samples. And that's something that you would expect, given that what you're basically doing here in noisy student training is you're making your model more robust against non-clean data. So you're making it into a more robust model. Another interesting observation is that after about 4 iterations, the improvement sort of stops. Okay, so that's this is the empirical test, and you can dive into the paper. There's lots more details about how they did it, how the models are set up. This is just a real quick drive-by. I do want to say a little bit before concluding about the improvement that the same authors. This is the other paper that I had, and by the way, there's a resources page at the end that you can get the deck, and all the resources are there. Has links to all these papers. The same authors repeated this. Well, did it slightly differently with a different base model, and they found they made massive additional improvements. And there's a couple of reasons that they made that improvement. The first was they went to a conformer architecture for the model itself. So the base model is simply better. It's larger, and it's got a stronger architecture than the original set. So some of the benefit is from there. But the other thing that's kind of cool is that they explicitly separately pre-train the encoders using unlabeled data before they even start the process. Before they begin the base model, they pre-train the encoders, and that's that intuition that I described at the beginning. And they use they also don't use balancing or filtering. And this is something that's sort of an interesting active area of research. What makes sense to do in terms of balancing and filtering? How do you do it? When does it make sense? When does it add? And what I will say is that my own personal bias is to do it, partly because it makes intuitive sense to me that it's going to improve generalizability. There's 2 things that you always have to think about. One is, how do you do on your test set? And then secondly, how confident are you that the results are going to generalize? Okay, so the algorithm there is really pretty much the same. I'm kind of running out of time, so I'm not going to go into any details other than to point out that it starts with a pre-trained. We pre-train the model with the unlabeled data, and you can see the results. You'll see the overall numbers here are massively improved. over what we were looking at before, and it's the same kind of pattern. It's interesting that they have a bunch of ablations that show things like the impact of whether or not you balance and filter, whether or not you add that external language model, what kind of impact that it has. This is an area of active research. People are doing lots of experimentation to determine kind of what is the optimal setup. So these results are significantly better, but most of the improvement is due to the base model itself being a lot better. But in addition, the separate pre-training of the encoder, I think it definitely contributes to their improved performance here. Okay, so conclusion. First, we've seen a couple of core semi-supervised learning ideas that I want to reinforce here. The first is that this notion of consistency, that self-supervised encoders can definitely be boosted just by providing unlabeled data. It's self-supervised. You don't need to, as long as you pump more data through those encoders, you're gonna get more benefit. Self-training works. It works, but you want to be careful because you do run the risk of confirmation bias. You do run the risk of ending up with results that don't generalize. Noise injection is an important part of the overall picture. It helps to reduce the tendency toward bias, and it also creates more robustness in the models that you're actually creating. Spec Augment does a nice job for noise injection, just completely ripped off out of image processing, applied, and there's lots of work in how to adjust the parameters, different ways of doing it. There's also different things that we can think about. This was just the first thing that we collectively, well, I shouldn't say that. It was an idea that has been applied, and there's probably lots of other ways that we could approach this. Balancing and filtering appear to have limited value when the starting model is very good. If the models are really good to begin with, which we saw in the last example, balancing and filtering don't seem to contribute that much to accuracy. My gut is they may still contribute to generalizability. Gradational filtering and augmentation are also mixed. I didn't really talk much about them, but it's in the initial study, they did ablations using them, not found in the noisy example. They both contributed. In the less noisy, not so much. Okay, I think that's pretty much all that I wanted to present. And at this point, I want to kind of open it up to, I have the resources here, which I won't go through, but they're all clickable when I get the thing. And now let me just open it up to any questions anybody has, any comments.
So we do have a couple of questions, at least in the chat.
If you want to answer a question, you can also raise your hand, because that's the whole point here, is a discussion. I might call people out on the team.
Fantastic.
Be prepared.
So we have a first question that it's more general. Is this the technology used by the apps with voice commands such as Alexa, Bixby from Samsung, Google? Do we know anything about that?
Honestly, I don't know the details of their implementations. So I know that they do that. I'll put it this way. Some of the core technology was contributed by Facebook and Google. I don't know the details of their implementation. I don't know, maybe somebody else does.
I mean, I don't want to call anybody out, but I think that I know that there is somebody that works in Alexa actually in this in this call. I don't know if
one thing I would like to I'd like to avoid sharing trade secrets and that kind of stuff on here. So I will say that definitely, we're all kind of fishing in the same pond here. The core underlying technologies, the transformers, the encoder decoder architectures, all that stuff is pretty common in the industry.
Fantastic. All right, we have another one. So this one comes from Alexander. He says, we have 10 hours of labeled data and 100,000 unlabeled data. In what ratio should we mix data on each generation phase? Yeah,
that's a really good question. And if you look in the papers, I definitely encourage you to look at both the base paper and the other ones that are in the references. And because the answer is you want to, it may require some experimentation. In the second paper, they used a constant 1:8 mixing ratio, and it seems that like 1:8, 1:10 is fairly common, but people have used different. And in the case of the first paper, they actually expand the gradational filtering enables the proportion of the sentences that the student gets that are pseudo-labeled to increase via iteration. So gradational filtering, as described in the first paper, makes that not constant. It actually increases over time. So this is something that it depends partly on the nature of your unlabeled set. It's something that you really want to, these are hyperparameters that you just want to tune. There isn't a universal answer. Although the most common that I've seen is in the range of 1:8 to 1:10.
Awesome. Thank you, Phil. Any other questions? Anybody raising their hand, showing their video maybe?
Or comments. People can make
comments. Yeah. Okay, so this one comes from Jacob. He says, do you have a high level intuition on how not balancing the pseudo label set provided increased performance? To me, this would lead to believe that this could lead to overfitting.
Yeah, I agree with Jacob. The only intuition that supports why non-balancing would give better performance is simply that balancing effectively reduces the example set, right? So balancing says an unbalanced set would, balancing takes things out of the set and replaces them with copies of other things. So there's maybe less information there for the model to train on. So intuitively, if the model is really good, I could see how non-balanced could perform as well. But I would share the kind of concern that you risk overfitting and you risk non-generalizability. The other sort of interesting thing, one thing that came to my mind immediately when I saw this stuff and saw how it was done and looked at a couple of other things and saw how people were doing it, was that it's a little bit weak to balance only based on the raw token distribution. I was expecting something, and I'd be curious about ideas that other people have about what are different ways that you could balance, what are different objective functions that you could set for determining that balance set.
Thank you, and thank you, Jacob. So Anna has a comment, I believe, in question. Aggressive spec augmentation on baseline supervised training method degrades accuracy, while the self-training with noisy student teacher training improves accuracy. What is the reason behind it?
Yeah, so we see that, like, for example, aggressive spec augmentation for supervised training, it degrades accuracy. So
accuracy, yeah, okay.
Accuracy, yes. And self-training with noisy student teacher training improves accuracy. So this is like two facts that I wanted to highlight and wanted also like to ask, and maybe, one more time, so we're all on the same page, like
yeah
happens. Yeah,
that's a good question. And first of all, the aggressive part, there's the hyperparameters that govern how much augmentation you do make a difference. If you do too much, if you imagine you mask the whole thing all the time, okay, sorry, it's never going to work. So how aggressive you are with that augmentation is definitely going to make a difference. And these are important hyperparameters to experiment with. The other thing is that if you look at the original, there's a paper before the noisy student training paper where spec augment is used outside of the noisy student training context, where you simply use it as a way of sort of augmenting some of the labeled samples that you provide to a model, to a single model. not to an iteration, an iterative stream of student models. You take a single model and you augment some of its training set, add noise to some of its training set. That's a little bit harder problem than if you're doing iteration and you've got a teacher model who's already supplied, at a previous iteration, pseudo labels. So it makes intuitive sense to me that it's a little bit more robust, but I think probably the key to your question comes down to how aggressive you are in that augmentation. And those, again, these are more hyperparameters that need to be fit carefully, and it's going to depend somewhat on how much noise there is already in the data, how good the model is, all that kind of stuff.
Okay, thank you for answer.
Awesome. Yeah.
Thank you, Anna. We have time for one more question. All right, Kyle, I think that you are muted, so fantastic. Go for it.
Well, I don't know how many times I've used the raise hand feature in Zoom, so that's pretty cool. Yeah, I wanted to ask what determines the optimal number of generations? So what causes because eventually the improvement stops, right? You said after 4 generations. So does that change if you have more data, or what are the factors that go into that?
Yeah, so that's a really good question. And the honest answer is I don't know. All I know is the empirical data that has been presented in papers and experiments that people have done. If you want my intuition about what's governing it, what's causing it to ultimately slow down improvement, it's that you're allowing the generations of student models to learn based on this process of giving them better examples, attaching pseudo labels, expanding your set of pseudo label data, and also allowing them to be tolerant of noise. It's intuitively obvious that eventually that's gonna, the new information, the new learning resource that is being provided is going to dry up, and they're not going to get better. For it to happen in like 4 iterations, that was frankly a little bit surprising to me. I was expecting to see longer trajectories there, and it could well be that by modifying the hyperparameters, by changing the techniques a little bit, and with different sizes of data, different distributions of data, we could see something different. That's a good question, long-winded answer to basically say I don't know.
You don't know, but there are certain intuitions about it.
Those are things that are and I'll add one other thing about the kind of why intuitively what I sort of see is going on in the model, that the teacher, you start off with, especially if you're actually doing filtering, where the teacher, there's a set of examples that the teacher is good at and that our model is good at. And what you're doing by adding noise to those and then providing the augmented set to the student, what you're doing is you're kind of expanding the range of problems that the model can easily solve. So you're making it, imagine that you're good over a certain range, it's making it good over a slightly larger range. And so you're now expanding the range of problems that the model is good at solving. And that's why the noise, that's the kind of that's the accuracy benefit of noise. The kind of generalizability benefit of noise is that you're not being inbred. You're not just recycling the same information back through the system and creating students that are just like their teachers.
I'm seeing a lot of good questions here. So Avneet, he says, supervised learning is a function over data. RL is a system that is acting in the real world and learning from it, and is closer to GAI. Is noisy student training in the middle of supervised learning and RL?
Well, that's a typically deep Avneet observation. Yes, I would say yes. And in fact, it's semi-supervised learning straight up, as is RL. Most RL, including the stuff that we're playing with all the time, is combines supervised and unsupervised techniques. And so it's not surprising. This is the difference is that I guess the kind of philosophical difference is that most RL is learning from sort of real experience in the domain that it's being applied. So it's learning the unsupervised part of RL, of most RL algorithms, comes from new data that it's seeing. This is sort of and it gets to Kyle's question, and it's actually a good observation that this is limited in a way that RL is not, because eventually you're going to run out of gas in kind of recycling the fumes, whereas in RL you're out learning in an actual environment of the domain. But
so Jacob has a comment on that question for Avneet, and he says, to me this seems a little more analogous to GANs, in which you have one agent trying to generate data which can trick the discriminator, and the discriminator tries to improve its detection.
Yeah, that's a good observation. Except that the teacher, except for the teacher is more, it's synthetic. The teacher is actually, it's the metaphor is a little. The teacher is, even though, like I said, when I first saw this and I saw the teacher injecting the noise and picking easy problems for it and injecting noise and giving it to the student, I said, oh, it really should be called nasty teacher training. Because the teacher says, oh, these problems are easy, let me make them harder and give them to my student. And then we end up with, we learn by imitation, we teach by intimidation. But in any case, it is a good observation.
Another one, and this might be the last one. We're using spectrograms for spec augmentation and not changing audio tracks. Is it just for performance?
If I understand the question, I will. The comment that I'll make is that it is not. I didn't really go into the details here, but it is a wrinkle that has to be dealt with. That in order to use spec augment in the front end of ASR models, you obviously have to have the spectrogram. So there is a little bit of a architecture fiddling, but the way that they do it in these examples is by making the model able to directly accept that stuff and do it in line. And the how efficient ways of doing the augmentation are important, but it can be done actually fairly efficiently in line.
All right. Well, with that, thank you, everybody. Thank you, Phil. Thank you for all the amazing questions. And again, as I mentioned, there's more of this coming up. And please tell your friends about it if you liked it. I know it's hardcore stuff, as I say, like deep technical stuff, but I think it's good. So Phil, anything for the last minute you want to say?
No, I just thank everybody for joining. And we at Nextiva are really, we're working with kind of, we're trying our best to be right on the cutting edge of the technology that's available, and all with the goal of just enabling our customers to have better conversations with their customers. That's all. That's the all and only.
All right.
Thanks, everybody.
Thank you, everybody, for joining from all parts of the world. I'm going to call out I see our Ukraine folks, Mexico people, everybody in the US. Thank you so much, and have a great day.